I am Pramatabhai, a PhD student from the Nuclear Engineering Department, and I also work at the Thermal Hydraulics Lab where we study the heat transfer and fluid flow in various nuclear systems. Today I'm going to talk about rainbow slitting deflectometry, which is a technique used to image various physical phenomena. First, I will talk ab- explain to you guys what Schlieren actually means and then delve into what the optical principles are involved, and then talk about the setup that is used for Schlieren imaging. And then I will talk to you about what rainbow and rainbow Schlieren deflectometry mean. And I will end it with certain application which is used in the scientific field. Schlieren simply means streaks in German. They are optical inhomogeneities in transparent materials which are not visible to the naked eye. Robert Hooke was the first person to observe this phenomena in the 17th century, where he used this lens setup to image the thermal air disturbances caused by a candle flame as seen below. He was able to differentiate like the laminar and the turbulent regions of a candle flame. Later on, August Doppler in 1984 developed the current Schlieren setup that is used in scientific laboratories throughout. With his apparatus, he was able to capture temperature differences less than 1 degree C, which was highly accurate. And also, he was the first to observe shock waves generated by electric spark. Now that we have established what clearing is, which are certain inhomogeneities that occur in transparent medium, I want to further explain what shaded imaging is. It is an optical technique used to visualize changes in the refractive index of transparent mediums, which often occur in fluids due to temperature or density changes. This technique can totally be explained by geometrical. Before we proceed on how this system works, I want to touch base on certain basic optical phenomena or principles that are used in setting up this technique. Refraction. When a ray of light passes through an interface where the refractive index changes, it gets deflected from its original path due to slight changes in its velocity. This deflection characteristics of light was first discovered by a Persian scientist called Ibn Saul at the Baghdad court at the Baghdad court in 1924 CE. As I said before, which is this is the main principle behind producing Schlieren image. As you can see in the image to the right here, the pencil appears to be bent when it's dipped in water because of refraction. Refractive index. Refractive index of an optical medium is the ratio of apparent speed of light in the medium to the speed of air or vacuum. The refractive index determines how much the path of light is bent or refracted when entering material. So refractive index is a way to quantify the amount of refraction that occurs when light passes through one medium to another. The refractive index is dependent on density, wavelength, temperature, etc. And the Gladstone and Dale empirical relation gives the relationship between the density and refractive index using this correlation here. For air, the Gladstone constant C here is around 2.23 into 10 to the power of 4 meter cube per kg. Next, I'm gonna explain how the experimental setup is laid out to obtain a Schlieren image. A point source of light is used to illuminate the test area and is placed slightly off-axis to the optical path of a concave mirror and is placed at a distance 2f from the optical of the concave. Then a knife edge is also placed at the 2f location, but now in line to the optical path. The area between the knife edge and the concave mirror makes the test section. Next, a screen or a camera is placed directly on the optical path behind the knife edge. As we know, because the knife edge is located at the 2f distance, all the light coming from the light source is focused on to the knife edge. Next, the height of the knife edge is adjusted so that approximately half of the light from the mirror gets blocked by the knife edge, which reduces the intensity of the image captured by the camera to at least half. When the object of interest, for example, a candle flame, is placed in the test area, which is the area anywhere between the concave mirror and the knife edge, the air becomes less dense around the flame, causing a change in refractive index. Therefore, the light ray passes through this region and gets deflected by a certain amount. As you can see in the image, the dotted line in the center here depicts the ray of light prior to introducing the candle flame. And when the candle flame is introduced into the test section, it gets deflected by a certain amount, as shown by the solid line. This deflection causes some of the light to get blocked by the knife edge, which otherwise would have passed onto the screen and formed an image. Consequently, the image intensity in this region changes, creating Schlieren bands. Here in the image below, you can see Schlieren bands that are caused due to shock waves that are produced and also because of the temperature change caused by the candle flame. This imaging technique can be used to visualize gas flow and identify laminar and turbulent regions. And also it can be used to qualitatively assess features like the shock wave strength, its location, and interaction with other flow structures. Although Schlieren is a powerful and inexpensive method to image density gradients, fine non-uniformities are really hard to distinguish in the grayscale images that are obtained using conventional Schlieren methods. Hence, an improved rainbow Schlieren method was invented to obtain colored images where fine details of varying densities are highlighted by a spectrum of colors. Here you can see a difference between an ordinary Schlieren image and a rainbow Schlieren. This increases the resolution of the image where we can get more detailed from. House with the team of NASA scientists introduced the term rainbow Schlieren to describe color Schlieren images created by simply replacing a rainbow filter in place of a knife edge, as mentioned previously. The variation of refractive index in the test section now makes the light deflect and fall onto different regions of the filter, thereby producing a colored image. When calibration, the color change in the image can be correlated to either temperature or density change. Therefore, we can now not only qualitatively analyze, but also quantitatively analyze the characteristics of an object of interest. To perform calibration, The filter is mounted onto an XY translation stage. A camera is focused onto the center line of the filter, and the RGB values of the image is uploaded. Then, using this formula here, the hue value is calculated. Next, the filter is either translated to the left or to the right by a certain amount. And again, the RGB value of that image is obtained and the hue value is calculated. So by repeating this process several times, a hue versus distance correlation can be obtained. Using the previously obtained calibration curve, which relates the translation distance to the image color, we can calculate the angle of deflection that is caused by the changes in refractive index in the test section using this formula below. And now with the angle of deflection, we can back calculate the change in refractive index that occurs in the test section that is caused by the object of interest. With this information, now we can calculate the change in density or temperature or other phenomena that we're interested in using the Glaston-Dale correlation that is mentioned in slide 3. Here I've listed certain applications where RSD is employed to quantitatively and qualitatively analyze certain setups. In the first example, the temperature above a hot plate is observed using RSD. The blue here signifies the temperature really close to the surface, which is really hot, and the red signifies the background temperature. So using RSD, the color change here can be correlated to the angle of deflection using the calibration curve, and the angle of deflection can be used to calculate the change in refractive index of air in this region, and the refractive index can be used to calculate the temperature or density in this region using the Gladstone correlation mentioned in slide 3. So using this technique, we can get the profile of temperature distribution of our flat plate. And if we have the temperature distribution, we can use that information to calculate the heat transfer coefficient using this formula here. The next example is RSD is used to analyze shock waves in supersonic flows and obtain various density profiles. And this can give information on how the structure behaves and also how it can be improved to reduce vibration. RSD can also be used to image two-phase flow, where a large fraction of light is absorbed by the liquid zone compared to the vapor zone. Conventional Schlieren imaging technique does not distinguish between the absorption and the refraction of light, making it really difficult to detect the liquid vapor boundary here. So the usage of RSD makes it easier for this application. This is the list of references that I use to understand and learn how RSD works. And yeah, that's it. Thank you. If you have any further questions, you can email me at this email address.